All right. Well, welcome back to the afternoon session, folks. And hopefully you're staying cool on this hot afternoon. I appreciate you joining me here. And let's try to get power through this discussion of photoelectron spectroscopy and try to get this done. Okay. So we left off this morning by talking about the need to acquire what's called the ionization energy. And we can acquire this ionization energy, and we saw then in the two schematics that I gave you in the slides above this one, the schematics I gave you, we saw then how by bombarding an atom with a high enough energy photon, if you take a photon with high enough energy and you collide it and you smash it into the atom, the electrons then will fly out of the atom with a kinetic energy that corresponds, kinetic energy that corresponds to their location around the atom. The closer the electron is to the atom, the more tightly it's bound to the atom, the less kinetic energy it has as it leaves. And so we were able to determine then the ionization energy if we know the energy of the photon, and this is where we left off with this morning. If we know what the energy of the photon is, which we can calculate for, and if we know the kinetic energy that it leaves with, which we can also determine as well, we can find then this ionization energy of that particular electron. And so what I was trying to point out, and so we did this problem this morning, and so what I was trying to point out to you then is, depending on the location of the electron, depending on where it is located at, it will have a different ionization energy. So imagine this then. So if we have then this generic atom right here, a generic Bohr atom right here, okay, and so we had an electron here, and let's imagine we had an electron here, and an electron in the third energy level. Okay, so we have an electron at each of these energy levels here. You're given here the energy, energy needed, energy associated with each one of those energy levels right there. Okay, and you can imagine then this is the energy that would be needed to remove the electron. So what we have here then is the ionization energy. Okay, the energy needed, and that's how we define the ionization energy. The energy needed to remove a particular electron from the particular atom. Okay. So with that said, then if you bring in and you hit each one of these electrons with a certain energy of the photon. Okay, so you take a certain energy photon, let's say this blue light here as an example. Remember, with photoelectron spectroscopy, we use either X-rays or photons from excited helium. We can also use ultraviolet UV rays. And so with that said, then we hit these here with the same energy photons. Okay, so let's see what happens if we hit it with the same energy. So all of these photons then will have the same energy. Okay, and so you can imagine this here. The one on the outside, the one furthest out, that an energy level 3, which we say only has about 1.5 electron volts, is held in place by you would need a 1.5 electron volts to remove this electron. Well, if let's say this electron, if the photon here was, say, let's just arbitrarily say that it's 15 electron volts or 15 electron volts. Remember, with helium gives you about 20 electron volts. Okay? So if you hit this with a 15 electron volts, you can imagine then that with this here, the amount of energy that it'll absorb. So it'll absorb about 1.5 electron volts, and that'll give us then, if this is 15 electron volts, okay, the amount of energy needed. So remember, what happens here is this electron here is bound to the nucleus. So here is your nucleus right here. There's your nucleus on the inside. It's bound to the nucleus with a certain energy. Okay, that potential energy that we talked about, that energy. So if it's bound to that by an amount that is about 1.5 electron volts, so we take that 15 electron volts, subtract 1.5 electron volts from it, okay, and what we get then is the kinetic energy. Now remember, the equation we're working with here is the energy of the photon is going to be equal to the ionization energy plus the kinetic energy, and that's what we did in the previous example there. We calculated for that one. Okay? So here what we're doing is if we have the ionization energy, we can calculate for the kinetic energy by subtracting the ionization energy from the energy of the photon. So with that said, then kinetic energy here, let's do that really quickly. 15 minus 1.5 electron volts, this would be 13.5 electron volts. that this one will have. Okay, let's go ahead and do the same thing for the second electron here. So we'll call this electron number 1. That'll be electron number 2, and this will be electron number 3. Okay, so this is the ionization energy for electron number 1. But I'm sorry, the kinetic energy electron number 1. Let's do the same calculation. Electron volts minus this time though. This could be 3.4 electron volts. So we can subtract 3.4 electron volts from here. And so the kinetic energy then for electron number 2, and let's go and do this, 15 minus 3.4 electron volts, you have 11.6 electron volts for this electron here. And then finally for the last electron, 15 electron volts minus, and the one in the ground state here, energy level 1 is going to be 13.6 electron volts. So therefore, the kinetic energy that the third electron has, 15 minus the 13.6, is going to be 1.4 electron volts. Okay. All right, so let's go ahead then. Let's write this in here. The kinetic energy that this electron leaves with then is going to be 1.4 electron volts. Kinetic energy here is going to be 11.6 electron volts, and the kinetic energy for this one is going to be 13.5 electron volts. Okay. All right, so know what we know about kinetic energy. So kinetic energy then is going to be 1/2 mass times v squared. So as the kinetic energy increases here, you can imagine then as the kinetic energy increases, and so we'll call this the velocity of electron 3. This will be the velocity of electron 2. This is velocity of electron 1. Okay. You'll notice then as the kinetic energy increases, so will the velocity. So therefore then, if we summarize here real quickly, I'm going to summarize on the side here. So the kinetic energy of 1 is going to be greater than the kinetic energy of electron 2, which is going to be greater electron 2, which is going to be greater than the kinetic energy of electron 3, which means then the velocity of electron 1 is going to be greater than the velocity of electron 2, which means then it's going to be greater than the velocity of electron 3. This is what we take advantage of here, folks. So what we do with photoelectron spectroscopy is that, and so I'm sorry, before I summarize here, and so this makes sense then, the electron that is held closest to the nucleus, the electron that's held closest to the nucleus will have the strongest ionization energy. We refer to this ionization energy then, when we talk about photoelectron spectroscopy, as the binding energy. It's the energy then essentially that binds the electron, so it's the binding energy here. That's what we refer to with the ionization energy. It's essentially the energy, so here's our binding energy. It's the energy that binds the electron to the nucleus. And it's that binding energy that we have to break in order for us to get the electron, get the ionization, to determine where the electron is located. So if the electron is closer to the nucleus, it will have a greater binding energy. Okay? And so if the binding energy or the ionization energy is greater, it's going to have a smaller, kinetic energy, and thus it'll move slower. Okay? And so that's what we can do by differentiating, by determining then. And so what happens is when the electrons fly into the, flies around the curve and ends up in the detector is able to determine then, based on its speed, the curvature of how fast it gets, how fast the electron, how long it takes the electron to move around that curve and get to the detector. We can determine that velocity right there. From that, we can calculate the kinetic energy. Okay? And so essentially then velocity is going to be displacement over time. That means if we know how far an object moves over a given time, then we can calculate its velocity. We know the curvature, we know it's the distance. Okay, it's such, and again, this is oversimplification, folks. Make sure you keep that in mind, but I think it gives you the idea. We know the curvature, we know the length of that curvature. The detector, remember, is over here. And so as the electron moves around here, depending on how long it takes to get to this point, then we can go ahead and calculate that velocity, and then we can determine it here. Okay. And so with that said, what we do with photoelectron spectroscopy is we take this information here and we correlate it back to the ionization energy. Okay. So if we know this, if we know how fast the electron moves, we can correlate it to its kinetic energy. And from its kinetic energy, we can relate it back to this binding or the ionization energy. And so what we do with this is we plot that ionization energy. Okay. We plot that ionization energy with the, and I'm going to go ahead and let's go against the relative amounts of those electrons. And this is what we get. This is the photoelectron spectrogram that we can obtain from that information. Okay. And so the position then, and if you look at here, this is the ionization energy, some diagrams, some of these graphs, and you'll see it labeled as binding energy as well. And the units here are in megajoules per mole. Okay. Unit of megajoules per mole is equivalent roughly to about, about a million joules, and the relationship between joules, and you don't have to do this conversion here, but 1 electron volt is roughly about 1.60 times 10 to the minus 19 joules. Okay, and we can do that conversion at another time. Okay, you'll learn how to do this conversion later. Okay. All right, but this is megajoules per mole. This is just joules here. So that's how we can see that, because you'll see ionization energy here listed for you in not only megajoules per mole, but also in electron volts per mole. So, okay. All right. So what we're seeing here then is that we have a higher ionization energy here. So this is megajoules per mole, and this is megajoules per mole, okay? Which means then these electrons here, so these electrons represented by this peak here will be closer to the nucleus. These will be closer to the nucleus, okay? And these will be further away from the nucleus since they have a smaller ionization energy, further from the nucleus. Okay, right. So you can imagine here's our nucleus, okay, and let's imagine that these are electrons here, okay. So then you can imagine that, let's say this corresponds to 2 electrons here, and we'll see then that the size of the peak represents the relative numbers, okay. So that's 2 electrons. We have 2 electrons closest to the nucleus. This next peak here is the same size, okay, but it's further out, okay. It's further away. It only has 3 megajoules, the ionization energy has 3 megajoules, so it would be out on the second energy level there. And that is how we correspond each one of these peaks to the location of the electron. Okay, and so make sure you keep that in mind, and that's what we will do moving forward. Interpreting these diagrams here are very simple, folks. I think interpreting them is very simple. I think making understanding what they mean is going to be a little bit more difficult, and that's why we went over. Okay, so you can imagine then these will leave with the higher kinetic energy. These will have a greater kinetic energy than these electrons here. Okay. Okay. So let's so this is kinetic energy for electron 3. This is the electron 12 here. So the kinetic energy here for the electrons at ionization 12 will be then less than the kinetic energy for these electrons at peak 3 here. Okay. Because these will leave with a higher kinetic energy. Okay. All right. All right, so with that said, then hopefully you can get that. Let's go ahead and let's answer a couple questions from the POGIL activity. Okay. So real quick then, what determines from the graph that we just did, what determines the position of each one of these peaks? This is number 3 on your, hopefully you got this. If you need to go get your work, please go ahead and do so. Go ahead and write this down then. What determines the position of the peak on each one of these here? If we take a look at them, what's going to determine the peak then is going to be the binding energy. Okay, so the ionization energy, energy of each electron, which then corresponds to the location. The location of each electron. And that's what determines the position on the x-axis. Okay. All right, very good. Let's take a look at number 4 then. What is indicated by the decrease in ionization energy from left to right? It just simply means then as you go from left to right, then the amount of energy needed to remove the electron will be less. Okay, so what is indicated by the decrease in ionization energy from left to right? The amount of energy needed to remove the electron will be less, and like we also pointed out, then the kinetic energy will be greater. Okay. So hopefully you had those written down as well. Okay. All right, let's go ahead then and let's continue on with the next one. Okay. Let's go ahead and do these two questions from the POGLE activity. We have then, what determines then the height, the intensity of each peak of photoelectron spectrum? Okay, and that is the number of electrons. Okay, so the number of electrons determines then the intensity of each peak. The higher the peak, the more electrons that it represents. Okay, so so it's the number of electrons at a particular energy level. Okay. Okay. And finally, what determines the number of peaks? The number of different electrons around the atom. Okay, so the height of the peak is determined by the number of electrons at a particular energy level. Okay, at a particular energy level, and the number of peaks then will be determined by the how many different electrons that we have. Okay, in the atom itself. Okay, and so that's how we can obtain then the electron configuration. So we have support now for the electron configurations that we've come up with for example, say the molecules that we worked with, or for the atoms that we learned about. Okay, so this is a very powerful tool that we can use in order to help us confirm what we said about the electron configurations themselves. Okay, so let's go ahead then and let me give you an actual photoelectron spectrum of nitrogen. So we did this. We saw that we saw dinitrogen. Okay, we did the molecular orbitals for dinitrogen. We did the electron configuration for dinitrogen. Okay, and so let me go ahead and give that to you as well, and let's compare here. Okay, so here was the electron configuration for dinitrogen: 2 electrons in the sigma 2s, 2 electrons in the sigma 2s antibonding, 4 electrons in this pi 2p, and then 2 electrons in the sigma 2p orbitals. Okay. And so here then we can correlate this to the energies, and make sure you keep this in mind. These electrons down here, and let's go ahead and take a look at this here. Okay. These electrons down here have a much higher energy level. Why? Because they're held closer to the nucleus. And so essentially what you want to imagine is this here. Okay. So what happens is, and I'm just going to draw these two, you can imagine this as being the 2 nitrogen nuclei. They sit in the middle. They sit in the middle of this new molecule. So this new molecule now is a molecule that's made of 2 nuclei. In much the same way you can imagine then with metals. Remember we talked about how metallic bonding occurs? A metal then is basically many metal atoms. Say, for example, silver. Okay, if you take a piece of silver, you have then many pieces of many silver atoms coming together, and they are basically one entity now made up of many, many nuclei, okay, with the electrons flowing throughout and the sea of electrons. And so you can imagine then that this is the same thing happening here. Now we have 2 nuclei in the center, and this is your dinitrogen. This is nitrogen 1, that's nitrogen 2. This represents then the sigma 2s. Okay, so you can imagine this represents the sigma 2s. And again, this is a really gross oversimplification, but I want you to see then that these energy levels here corresponds to these energy levels here. This represents in the sigma 2s star, okay, and so forth. Okay? And so the ionization energy, the binding energy here for the, we're given the binding energy for the sigma 2s star, and that's 18.6 electron volts. Okay? The reason why we don't even include these electrons here, because they're held so close to the nucleus, they're held so strong into the nucleus, it's that you can't remove them. You can't remove them, and so therefore we don't have enough energy. We can't shoot any photons with it that has a large amount enough energy to eject these here. However, we can eject these, and so you can imagine as we move out from this, we have then the pi out here. We have the pi 2p molecular orbitals. Okay, and so in this particular molecular orbital here, we have our 2 electrons. Okay, and if we want to use our Bohr model here in order to kind of see this, we have 2 electrons here, 2 electrons here. We have 4 electrons, 2, 3, 4 electrons sitting out there. Okay, and remember these are all degenerate orbitals, so all these electrons are equal in energy. Okay, all right. So with that said, then we will if we hit each one of these electrons here. Oh, sorry. let me go ahead and erase this here. So we hit each one of these electrons here with a certain photon of energy. Okay, so let me try to finish up here. We hit it with a certain photon of energy. So there is our energy there for our photon. Okay. We will eject these electrons here. Okay, and so what you'll notice then is that this corresponds, these two electrons corresponds to this peak right there. Okay, so that means then this is the sigma 2s antibonding. These, then we have these next four peaks. These peaks here, these four peaks correspond roughly to the pi 2p, okay? And then this one here represents then the sigma 2p electrons. Now, the intensity of these electrons, the peaks here, aren't quite what we expected, but this is an actual photoelectron spectrum here, and it's a little bit more complex than what we see. Okay? And so we look at a simplified version of what we have here. Okay, then you can kind of trace what we'll have for the atoms that we'll consider. Okay, all right. So with that said, then what we're going to do then, and so like I said, nitrogen was, but I'm sorry. Let me go back here really quickly then. So that's how we know then. Remember, we said that there's two different ways that the molecular orbitals can set themselves up. It's this data right here. It's this data right here that allowed us to confirm then that we had 4 electrons rather than 2. So remember, the option here was to have the sigma 2p sit below the pi 2p. The electrons here, we see these peaks here, and that's how we know then that the electron configuration actually follows this order rather than the flipped order that we saw for oxygen and the halogen. Okay. All right. So with that said, then there's the data that I've been talking about. I know that you've been wondering where this whole idea behind photoelectron spectroscopy, how this data confirms our molecular orbitals and how we can determine the order of the electrons. Okay. So here, there's the data that we use to confirm that this was the correct electron configuration for nitrogen, rather than having these two here flipped around. Okay. All right. So what we're going to do tomorrow, and I know that I'm asking a lot of you, but folks, hang in there. We're almost done with this. What we're going to do tomorrow is we're going to learn how to interpret, and I'm going to go ahead and finish this up and then start Beer's Law tomorrow. Hopefully start Beer's Law tomorrow. But we're going to interpret simpler spectra, and we're going to interpret the spectra for atoms, okay? And the spectra for molecules is going to be a little bit more complex if you saw for dinitrogen. So we're going to limit ourselves to the discussion of atoms, and then you'll see then that the electron configurations that we came up for atoms can be supported by data from photoelectron spectroscopy, and that is why it's such a powerful tool, okay? All right, very good, folks. And so we'll pick up with this discussion tomorrow, okay? And then we'll practice it a bit more in class tomorrow at lunch, okay? All right, folks, have a good afternoon, and I will see you tomorrow, and we'll learn more about photoelectron spectroscopy then, okay? I'll see you tomorrow.